For over 200 years, the world of physics was dominated by the ideas of Sir Isaac Newton. Back in 1687, Newton wrote a book called Mathematical Principles of Natural Philosophy. In that book, he described how everything in the universe moves, thanks to 3 laws of motion and a law of gravity. According to Newton, everything in the universe pulls on everything else. The larger the mass, the stronger the pull. That pull is what we call gravity. Newton's ideas explained a lot. They told us why apples fall to the ground and why the moon orbits the Earth. And it worked, but not perfectly. They didn't explain everything. Some questions remained unanswered. Why do objects pull on each other at all? What is the source of gravity? Also, there was a tiny problem with Mercury's orbit, the smallest and closest planet to the Sun. Its path around the Sun has a strange wobble in its orbit that Newton's laws couldn't fully explain. Fast forward to the early 1900s. A curious man named Albert Einstein was working at a patent office in Switzerland. In 1905, Albert Einstein introduced something called the special theory of relativity. This theory explains how objects move when they're in an inertial frame of reference, which means they are not accelerating, and what happens when they approach the speed of light. But this theory had a limitation. Special relativity only worked in situations where gravity could be ignored, and where objects moved at constant speeds and are not accelerating. So, what about falling objects? And what about gravity? For years, he struggled to extend his theory to include acceleration and gravity. Then, in 1907, while working at the Swiss Patent Office, he had what he called the happiest thought of his life. Einstein did a crazy thought experiment while watching a worker climb a ladder. He imagined what the worker would feel if he fell from the ladder, and although that's not exactly a cheerful thought, it helped him realize something powerful in theory. If the worker were in free fall, that is, falling freely under the pull of gravity and nothing else, he wouldn't feel his own weight at all. To him, it would feel as though gravity had completely disappeared. He wouldn't feel the ground pushing up on his feet, because there's no ground under him. There's nothing to resist his fall, so he'd feel weightless. That's when Einstein began to stretch his imagination even further. What if, while falling, the worker took a ball out of his pocket and let it go? From his point of view, the ball wouldn't fall. It would just float right there beside him, calmly, as if glued in space. In fact, everything around him would appear to float. It would look exactly like what astronauts experience in space. Even though both the worker and the ball are falling together under gravity, there's no way for the worker to tell that he's falling, because everything around him is falling at the same rate. This simple but deep thought experiment gave Einstein a thrilling insight. Maybe being in free fall is not so different from being in space where there's no gravity. Maybe gravity isn't just a simple force pulling things down. Acceleration and gravity, in fact, be the same thing. This is what is called the equivalence principle, one of the cornerstones of general relativity. To understand it better, Einstein did more thought experiments. Imagine you're inside a completely sealed room. No windows, no doors, no way to look outside or know where you are. Now suppose that room is sitting still on the surface of the Earth. If you try to measure your weight, maybe by standing on a weighing scale, you'll get a normal reading. The scale will push up against your feet, and you'll feel your weight just like you always do. Now, here's where it gets interesting. Imagine the exact same sealed room, but this time it's floating in deep space, far away from any planet or star. But instead of being still, the room is being pulled upward with constant acceleration, maybe using an engine with the same acceleration as Earth's gravity. 9.8 meters per second squared. Inside the room, you again stand on the same weighing scale. To your surprise, the scale will give you the same reading. It still pushes up on your feet. And from inside the room, it feels exactly the same as it did on Earth. It's just like when you're sitting in a bus that suddenly accelerates, you feel a jerk, as if you're being pushed back, even though nothing is actually touching you. That sensation is because of the acceleration of the bus, and it can easily be mistaken for a force, something like gravity. There's no experiment you can do inside that sealed room to tell whether you're standing still on Earth or being accelerated in space. This is called the equivalence principle, where the effects of gravity and acceleration can be completely identical, depending on your point of view. To the person inside the room, gravity and acceleration are two sides of the same coin. This meant that instead of thinking of gravity as a force pulling us down, maybe we could think of it as Earth is accelerating upward beneath us with an acceleration of g. But Einstein wasn't done yet. He took the thought experiment one step further. Imagine you're still inside that same sealed room. This time, you decide to shine a beam of light from one side of the room to the other. We all have heard in our school that light travels in a straight line, right? So, if the room is sitting still on the surface of the Earth, the beam of light travels in a straight line, as you would expect. Now imagine the same room again, but this time it's inside that accelerating spaceship, moving upward with a constant acceleration of g. Now look at this part clearly. While the light is crossing the room, the floor is moving upward. So by the time the light reaches the other wall, it hits slightly lower than where it started. From inside the room, it looks as if the beam of light curved downward. Although from the perspective of the observer outside the room, the light traveled in a straight line, or this one. But for the person inside the room, the light started from this point, near his ear. But due to motion of the room upwards, it reaches this point on the other side of the room, which makes it looks as if the beam of light curved downward. Now, remember Einstein's earlier insight. If acceleration and gravity are truly the same, then this bending of light shouldn't just happen in a spaceship. It should also happen in a gravitational field. In other words, gravity should be able to bend the light. This was a revolutionary idea. Until then, light was always believed to travel in perfectly straight lines, no matter what. But now, Einstein was suggesting that gravity could actually bend the path of the light. Einstein couldn't stop thinking about it. He thought, why would light, something that's supposed to always move in straight lines, suddenly appear to bend? That didn't feel right. But then he had a brilliant thought. What if the light wasn't actually bending at all? What if the light was still taking the straightest possible path, but space itself wasn't flat anymore? He imagined that space could be curved, the same way a sheet of paper can be flat or rolled. So if space was curved, then the path of light, which always tries to go straight, would appear bent to someone like us, living inside that curved space. And that was another breakthrough. The big one. Einstein realized that maybe gravity isn't a mysterious invisible force pulling things down, like Newton had said. Maybe what we call gravity is just the result of mass bending the fabric of space and time. One of the most famous ways to visualize this is with the trampoline analogy. Imagine a large, stretchy rubber sheet, like a trampoline. Now, place a heavy ball in the center. The sheet sags under its weight. Now roll a smaller ball across the sheet. As it approaches the dent, it begins to curve around the heavy ball. Not because there's an invisible string pulling it, but because it's following the curved path of the sheet. A heavy object like the sun doesn't pull Earth toward it using a force. Instead, it bends the space around it, and Earth simply moves along that curved space. Even light follows this curved space. To put this into precise mathematical language, Einstein spent nearly 8 years developing a set of incredibly complex equations. Equations that could describe exactly how mass and energy curve space and time. These became known as the Einstein field equations. And finally, in the year 1915, Einstein presented his new theory to the world, the general theory of relativity. A theory that didn't just describe how gravity works, but redefined what gravity actually is. Of course, it's important to mention, the rubber sheet example is just a two-dimensional visualization. It's a helpful way to picture how mass can bend space, but in reality, space isn't a flat sheet. It's three-dimensional if you just consider space, or rather, four-dimensional when you include time, which is why it is called a space-time fabric. You will say, "Hey, Brain Station, this sounds like a science fiction film." In science, a theory isn't enough, no matter how beautiful it sounds. We need proof. Solid, testable, observable proof. That proof came in the year 1919, during a total solar eclipse. A British astronomer named Arthur Eddington led an expedition to test one of Einstein's bold predictions. He aimed to photograph stars that appeared close to the sun in the sky. Under normal conditions, the sun's bright light would wash out the view, but during a solar eclipse, the sun's light is blocked, and the background stars become visible for a brief moment. Einstein's theory had said that the sun's mass should bend the space around it, and since light follows the curves in space, the light from those background stars should appear slightly shifted, as if the stars had moved a little. And when the photographs were developed and analyzed, that's exactly what they found. The stars did appear slightly displaced from their usual positions, and the amount of shift matched Einstein's predictions perfectly. Whoa! Awesome! This was the first direct evidence that gravity bends light. Not because light is changing direction, but because space itself is curved. What do you think? Is he done? Not yet, folks. Einstein didn't stop at the bending of space. His theory of general relativity went further. Imagine two friends. One is floating in deep space, far from any stars or planets, and the other is standing near a massive planet. Both of them shine a flashlight at the same time. The speed of light must be the same for both of them. That's a fundamental rule of physics. But here's the twist. Near the massive planet, space is curved. So the light has to travel through stretched space. Now, in order to reach the same point, this light has to travel less distance, and this light has to travel more distance. But speed is the same. So the time for the light to reach this point for this observer has to increase as compared to his friend in empty space. This means to balance everything out, time itself slows down for the person near the planet. That's why gravity slows down time, to keep the speed of light the same for everyone, even in curved space. This effect is called gravitational time dilation. This isn't just theory. We've measured this. For example, clocks on the surface of the Earth tick slightly slower than clocks on satellites orbiting far above. These satellites experience weaker gravity, so their clocks move just a bit faster. This difference is tiny, but it's real. In fact, the GPS system in your phone has to constantly adjust for this effect. If it didn't, your map location would be off by kilometers in just a single day. Einstein's theory of general relativity didn't just change science, it reshaped how we think about reality itself. If you enjoyed this video, please don't forget to like, share, and subscribe to our channel. Also, you can support my channel by joining our community and becoming a member. So good. Ooh.